Hello! We will look at a small modification to an example from the lectures. In Lecture 01C, we have a shipping example where there are 6 types of crates and we want to see how many of each type we want to ship. There was a total weight limit of 10,000 pounds. Now, one condition that is explained in the lectures is we must take at least 4 crates of type 1 or 2 or 4 crates of type 5 or 6. Suppose we make a small modification on this condition. Suppose we must take a total of at least 4 crates of type 1 or 2, or take a total of at most 4 crates of type 5 or 6. And we want to know how can this be formulated. We start by recalling what was the solution to the original problem. We had variables x1 to x6 representing the number of crates of each type. In the original problem, we define a new binary variable y so that y equals 1 implies the first condition holds, x1 plus x2 is at least 4. And y is equal to 0 implies that the second condition holds, x5 plus x6 is at least 4. And we added the new constraints, x1 plus x2 is at least 4y, x5 plus x6 is at least 4 times 1 minus y, and y is 0 or 1. Now in the new problem, we have changed at least to at most in the second condition. So the question is, can we simply change this inequality to solve the new problem? That is, we flip the sign to get x5 plus x6 is at most 4 times 1 minus y. And the answer is no. And that is because when y is equal to 1, where the first condition is supposed to hold, we have x5 plus x6 is at most 0. This forces x5 and x6 to be 0. This is an unintended consequence of setting y is equal to 1. It restricts the variables of x5 and x6 unnecessarily. Now what we want is, if y is equal to 1, then x1 plus x2 is at least 4. And if y is equal to 0, then x5 plus x6 is at most 4. We still want to keep the first constraint, x1 plus x2 is at least 4y. For our second constraint, we want to have x5 plus x6 is at most something. But what could this be? Well, if y is equal to 0, then we want this upper bound to be 4. But if y is equal to 1, then there should not be any further restriction on x5 plus x6. So one way to avoid any restriction here is to try x5 plus x6 is less or equal to a very large number. But how large should this number be? It should be large enough so that any feasible solution is not eliminated by this number. In this particular problem, we can set 10,000 to be this number. Remember that this problem restricts the total weight to at most 10,000 pounds, so we will never send more than 10,000 crates. So what we can do is, we set x5 plus x6 to be less than or equal to 4, and when y is equal to 1, we will add a very large number. So that gives us this inequality. x5 plus x6 is at most 4 plus 10,000 y. And this is how we would solve the problem. Now let's write down the full solution. We defined a binary variable y to represent these conditions. If y is equal to 1, then x1 plus x2 is at least 4. If y is equal to 0, then x5 plus x6 is at most 4. To achieve this, we will add these constraints to the IP. x1 plus x2 is at least 4y, and x5 plus x6 is at most 4 plus 10,000 y, and y is either 0 or 1. We now justify our constraints. We see that there are two cases, either y is equal to 1 or y is equal to 0. When y is equal to 1, we have the constraints x1 plus x2 is at least 4, and x5 plus x6 is at most 10,004. The first inequality is what we wanted when y is equal to 1. The second inequality is redundant since it is impossible to ship more than 10,004 crates in this problem. In the second case, when y is equal to 0, we have x1 plus x2 is at least 0, and x5 plus x6 is at most 4. The second inequality is what we wanted when y is equal to 0. The first inequality is redundant since we already have x1 and x2 are both at least 0. So this formulation is correct.